Picture a machine the size of a school bus, falling through the dark at 6 miles a second, aimed at a frozen world 500 million miles from home. It's the year 2000, and the Galileo spacecraft is about to skim past Europa, one of Jupiter's moons, close enough to count the cracks in its ice. On board, a magnetometer is doing what it always does, reading the invisible field around it, sketching numbers no camera could ever see. Europa is supposed to be a dead ball of frozen rock and water, silent, inert, going nowhere. Dead things don't push back. But as Galileo threads the gap, the needle starts to bend, not a twitch, not noise, a steady, deliberate lean toward the moon, as if something below that white shell felt the spacecraft coming and answered. The engineers had seen the field of Jupiter itself, monstrous and loud. This was different. This was small, local, and it was pointing back. And here's the part that should raise the hair on your arms. Instruments do not flinch at dead rock, and this moon made 3 of them flinch at once. At first, the team called it drift, the kind of jitter you scrub out of any dataset. But it didn't wander like noise. It sat there, steady, holding a curve that bent the same way every time the numbers came back. Then someone lined it up against Jupiter's position, and the room went quiet. The reading rose and fell with the giant planet, tracking it, answering it. That's not what static does. Static doesn't keep time with a world 400,000 miles away. A magnetic field was leaning back against Jupiter's pull, pushing where it was pushed, flexing on a schedule. The shape was too clean, too responsive, too alive with someone else's rhythm to be an accident of dead ground. And once you see a field behave like that, you have to ask what's making it, because the physics only allows a short list of answers. To make a field like that, you need something buried, something liquid, and something vast. So think about what that means. A magnetic signature like the one Galileo picked up doesn't come from rock, and it doesn't come from ice sitting frozen and still. It comes from a conductive fluid moving in Jupiter's magnetic field, a salty ocean carrying charge the way seawater does back home. And here's what makes the skin prickle. Europa orbits about 780 million kilometers from the Sun, 5 times farther than Earth. Sunlight out there is roughly a 25th of what we get. By every rule you'd expect, water on that surface should be locked solid, no exceptions. Yet the signal insists otherwise. Below a shell of ice, hard as granite in the cold, something stays liquid, not a puddle, not a trapped pocket, but a layer wrapping the whole moon, sealed under kilometers of frozen crust, dark and quiet and moving. That's the part that stops you. A world too far from any warmth to justify it, hiding an ocean anyway. And when scientists finally worked out how deep that water might run, the number they eventually landed on does not sound like a moon, it sounds like a planet. Europa is smaller than our own moon. Line it up next to Earth and it barely registers. A pale marble you could lose behind a fingertip. So the numbers don't feel like they belong to it. Under that shell, the ocean might run 60 to 150 kilometers deep. Not a lake, not a sea. A layer of liquid water wrapped clean around the entire moon, from pole to pole, with no shore anywhere. Do the math on that volume and it climbs past everything Earth holds. Every ocean, every trench, every drop in every sea we've ever mapped, and Europa may be carrying 2 to 3 times more, tucked inside a body a quarter of our width. And none of it ever sees the sun. There's no surface to break, no sky above the water, just kilometers of ice pressing down like a lid that was never meant to open. Whatever moves down there has never known light. So sit with the shape of that, a hidden ocean bigger than our whole planets, sealed in permanent dark on a world so small it hides behind your thumb. Water is not the scary part, and warmth is not the scary part either. For 400 years, Europa was nothing, a speck in a telescope, a name in a footnote, one of the countless moons a student memorizes and forgets by the next exam. Nobody lost sleep over it. Nobody had a reason to. Then, one by one, every reason to ignore it fell apart. The idea that it was frozen solid, dead rock under dead ice, stopped holding up. The assumption that nothing could survive that far from the sun cracked. The belief that oceans need sunlight to matter turned out to be wrong. It wasn't a single discovery that changed the story. It was a collapse, a pile of safe assumptions that had stood since Galileo, all giving way inside a few short decades, until the harmless dot became something scientists could not stop staring at. And when the dust settled on all of it, the conclusion was hard to say out loud. That quiet little smudge behind your thumb, the one nobody bothered to look at twice, had become the most promising place in the solar system to find something alive. So start with the face itself. Europa is crossed by long reddish lines, thousands of miles of them, like cracks that bled and scabbed over. Nobody has held a sample. The best guess for that color is salt and sulfur, dragged up from below, chemically wrecked by radiation. But the honest answer is that we're still arguing about it. Then there are the plumes. In 2013, Hubble caught what looked like water vapor jetting 125 miles off the surface, then vanishing. Later data hinted at more. If those eruptions are real and repeating, something down there is under pressure and finding its way out. And hanging over all of it is the radiation. Jupiter's magnetic field is monstrous, and Europa sits right inside the worst of it. Standing on that surface, an unshielded human would absorb a lethal dose in minutes, maybe less. It would sterilize you before you finished looking around. Reddish wounds, eruptions caught mid-air, a killing field of radiation overhead. We're not solving any of these yet, just laying them on the table. Each of those clues points at the same door, and behind the door is water. Ask a planetary scientist about life on Europa and watch how carefully they talk. They don't say yes. They say the conditions are interesting, then they change the subject. But if you push, the same comparison keeps surfacing, quietly, like they'd rather you reached it on your own. On Earth, we always assumed life needed the sun. Then in 1977, a submersible found the exact opposite at the bottom of the Pacific, 2,500 meters down, in total darkness. Cracks in the seafloor were pumping out mineral-rich water at 400 degrees Celsius, and clustered around them was a thriving world that had never felt a single ray of light. Those hydrothermal vents run on chemistry, not sunlight. The rock feeds the microbes feed everything else, and many researchers now think this is where life on Earth actually started. No sky, no warmth from above, just water meeting hot stone in the dark. Now hold that picture against Europa, a deep ocean, a rocky floor, and very likely the same kind of heat leaking up through the cracks. The one place on Earth where life may have begun without the sun looks a lot like the seabed of a moon 500 million miles away. If that comparison holds, then Europa is not empty, and that thought is hard to unthink. So here's what this episode is, and what it isn't. We're not going to tell you a whale swims under that ice, or that anything with eyes is looking up at the frozen sky. Nobody knows that. Nobody can. Not yet. What we can do is follow the evidence right up to the edge of the question. The chemistry, the heat, the salt water in motion, the energy that could feed something down there in the dark. Every piece stacks a little higher, and every piece is real. Think of it like standing at the rim of a cliff at night. You can't see the bottom, but you can hear water moving far below, and you can feel how far the drop goes. That's where we're headed. To the edge, where the instruments stop and the imagination starts. We'll show you exactly what's been measured and exactly where the measuring runs out. The view, not the answer. And it is one of the strangest views in the solar system. But to understand why this is terrifying, you have to go back to when it was nothing at all. So here's the road we're going to walk. 4 centuries, start to finish. It begins with a faint smudge in a handmade lens and ends with a spacecraft engineered for one purpose, to find out what's moving beneath a shell of ice. Along the way, the story keeps changing shape. A curiosity becomes a puzzle becomes a target, and a target becomes one of the few places off Earth where scientists will actually say the word life without flinching. We'll trace how a dot nobody could resolve turned into a world with more liquid water than every ocean on our planet combined. We'll follow the flybys, the magnetic readings, the plumes caught rising off the surface. Each step gets us closer, and each step raises the stakes. But we're going to keep the ending sealed for now. What's down there and why it should unsettle you comes later. First, we rewind all the way back to before anyone knew Europa existed at all. It starts with a man, a cold night, and 4 points of light that were not supposed to be there. Padua, Italy, the winter of 1610. The nights are long and bitter, and the city sleeps under a hard frost. In a rented house near the university, a man in his mid-40s carries a slender tube out into the cold, its lenses ground by his own hand. His name is Galileo Galilei, and the instrument he's holding barely deserves the word telescope. It magnifies maybe 20 times, less than a cheap pair of binoculars you could buy today. The glass is imperfect, the image swims, and his fingers are going numb around the frame. But he points it at Jupiter anyway, the brightest thing hanging in that January sky. Nobody has ever really done this, aimed a lens at a planet and written down what they saw night after night. There's no map for what he's about to find, no textbook, no one to ask. And there, clustered close beside that bright disk, he notices something odd, little pinpricks of light, faint and sharp, sitting in a neat line. The man at the telescope thought he was looking at stars, and he was completely wrong. It's January 1610, and the telescope in his hands is barely more than 2 lenses in a tube, magnifying maybe 20 times. By modern standards, it's almost useless, a toy you could beat with a cheap pair of binoculars today. But Galileo pointed it up on a clear Italian night, and for the first time in human history, someone saw the heavens with a little more resolution than the naked eye. 4 faint dots hung near Jupiter, tiny and sharp against the dark. He sketched their positions carefully, 3 on one side, 1 on the other, small marks in ink beside the bright disk. Nothing about them seemed remarkable that first night. They looked like background stars caught in the same patch of sky. So he did what any careful observer would do. He waited, and he looked again the following evening, and then the evening after that, tracing those same little points and comparing them to his earlier drawings. He assumed they were fixed stars, until they refused to stay still. On the first night, the little points sat in a neat line beside Jupiter, 3 of them where he expected stars to stay put. The next night, they'd shuffled. One had jumped to the other side of the planet, another had vanished entirely, and the spacing was all wrong for anything fixed to the sky. Stars don't do that. Stars hold their positions for centuries, which is exactly why we call them fixed. But these dots kept sliding back and forth across Jupiter, night after night, sometimes clustered on one flank, sometimes strung out on the other. And slowly, the only explanation left standing sank in. They weren't drifting past Jupiter, they were circling it, swinging around the planet the way the moon swings around us, tethered to something that wasn't Earth. Sit with how strange that was in 1610. Everyone knew everything orbited Earth. Now here were 4 little worlds looping around a body millions of miles away, ignoring us completely, and a man with a homemade tube had just watched it happen with his own eyes. One of those 4 moving dots is the reason this video exists. Think about what that actually meant. For thousands of years, the sky had a fixed rule at its center, and that rule was us. Earth sat still, and everything else, the sun, the planets, the stars, wheeled around it in perfect obedience. Those 4 dots broke the rule quietly. They didn't circle Earth, they circled Jupiter, a world that itself was clearly moving across the sky, and they never once glanced our way. If moons could orbit something other than Earth, then Earth wasn't the anchor holding the whole cosmos in place. That crack spread slowly, but it spread. Over the next few decades, the idea that we sit at the middle of everything started to look less like fact and more like habit. We weren't the center, we were one more object, moving through a much larger and stranger arrangement than anyone had drawn. And here's the strange part. Of those 4 dots that helped rewrite the sky, one of them, the second one out, would keep its own secrets far longer than the rest. For 300 years, that speck would tell us almost nothing. So where does the name come from? It wasn't Galileo who picked it. He wanted to call his 4 moons after his patrons. the Medici family, and for a while that stuck. The names we use now came later, from an astronomer named Simon Marius, who reached for Greek myth instead. Europa was a Phoenician princess, and the god Zeus wanted her, so he did what gods in these stories do. He turned himself into a gleaming white bull, mixed in with her father's herd, and waited by the shore until she climbed onto his back. Then he bolted for the water. He carried her across the open sea to the island of Crete, a woman on the back of a bull, moving over the waves toward a place she'd never chosen to go. That's the myth stitched into this moon's name. Pick that thread apart, and it's almost too neat. A world named for someone carried across a sea, hung on a moon we'd one day suspect of hiding an ocean under its skin. But nobody knew that yet. The name was a coincidence, or at least everyone assumed it was. For a long time after that, Europa didn't change. Every telescope that turned toward Jupiter found the same thing Galileo had, a little spark near a bright disk, blinking in and out as it circled. Better lenses came, bigger tubes, ground glass, mounts that tracked the sky. The spark stayed a spark. Astronomers in the 1600s and 1700s could time when it slid behind Jupiter and when it came back out. They could clock its orbit to within minutes. They could even use those eclipses to estimate the speed of light. But nobody could see a single mark on it. Think about what that means. You can watch something for centuries, night after night, log every position, and still know nothing about what it actually looks like. It was a point on a chart, a number in a table, a name in a book. For nearly 300 years, that's all Europa was, a pale dot that never resolved, no matter how good the glass got. Astronomers could measure its size and its orbit, but its face stayed hidden. So astronomers went after the light itself. If you can't see the surface, measure what bounces off it. And Europa bounces back a lot. Its albedo sits around 0.64, meaning it reflects roughly 2/3 of the sunlight that hits it. For comparison, our own moon reflects about 12%. Europa is nearly 5 times brighter, gram for gram, than the grey rock we stare at every night. Something up there is clean and pale and almost mirror smooth. In the solar system, that usually points one direction. Then came the temperature. Out at Jupiter's distance, sunlight arrives weak and Europa's surface runs brutally cold, around 110 K at the equator at noon and closer to 50 K near the poles. That's roughly minus 160 degrees Celsius on a warm day, colder than anything Earth has ever recorded. Bright and frigid, reflective and frozen. Put those two readings side by side, and the picture almost draws itself. Whatever covers Europa is most likely water ice, spread across the whole face of the moon. But that only described the top layer, the part catching the sun. Ice on the surface was interesting, but ice was supposed to be the whole story. For most of the 20th century, there was a simple rule about moons, and it worked almost every time. Size decided everything. A small world had a small budget of heat, and once that heat leaked away into space, the world was finished. The logic came from basic physics. Heat comes from a body's interior, left over from formation and from radioactive decay in the rock. A big planet holds that warmth for billions of years, but a small moon has too little volume and too much surface area, so it bleeds heat fast and cools all the way through. So the expectation for a moon a few thousand kilometers across was almost boring. A frozen ball, no churning inside, no fresh terrain, no reason for anything to change. Whatever it looked like today, it had looked that way for ages, and it always would. Our own moon fit the picture. So did most of the little worlds glimpsed through telescopes, cratered and still, like fossils that stopped keeping time long ago. Every scientist knew moons this small had gone cold billions of years ago. Europa doesn't travel alone. It's one of 4 big moons Galileo spotted, and each one turned out to be its own kind of world, wildly different from the next. Line them up, and you're looking at a family portrait where no two siblings resemble each other. Closest in is Io, a moon squeezed so hard it never stops erupting. Hundreds of volcanoes paint it in sulfur yellows and reds, and plumes climb 300 kilometers off the surface. It's the most volcanically active place we've ever found. Farthest out sit the giants. Ganymede is bigger than the planet Mercury, the largest moon in the whole solar system, wrapped in ancient grooved terrain. Callisto hangs beyond it, dark and scarred, its face so crowded with craters that it's basically kept the same weathered look for 4 billion years. And Europa? It rides the second orbit out, tucked between fiery Io and the two old giants. Smaller than our own moon, quiet-looking, easy to overlook in that lineup. Sitting between a world on fire and a world of ice would turn out to matter enormously. Jupiter isn't just big. It's more massive than every other planet in the solar system put together, over 300 times the mass of Earth, a ball of gas so heavy it very nearly became a star. That mass does something to everything nearby. Jupiter holds a swarm of 90-plus known moons on tight leashes, whipping the inner ones around in days instead of years. Europa laps the planet once every 3.5 days, moving faster than any world has a right to. Stand on Europa and Jupiter fills a huge slice of the sky, a striped face that never sets and never shrinks. Its pull reaches down through the ice and never lets go, the same way the sun rules us, except close and constant and enormous. So Europa doesn't drift through space on its own terms. It's held, steered, worked on by a force it can't escape and can't answer. That grip is not gentle, and Europa never gets to rest. So look at the face it shows us. Even in the early images, blurry and low resolution, something about Europa doesn't add up. The other moons out here are covered in wounds, pockmarked, cratered, chewed up by billions of years of impacts. Ganymede wears them. Callisto is practically buried in them, thousands of overlapping scars, stacked so deep you can't tell where one ends and the next begins. That's what a 4-billion-year-old surface is supposed to look like out here in the shooting gallery around Jupiter. But Europa comes back almost blank, smooth, the kind of smooth that shouldn't exist on a body that's been sitting in the same violent neighborhood for the same 4 billion years. Every moon around Jupiter got hit by the same rocks, the same comets, the same debris. They all kept the record. Europa somehow doesn't have it. The bruises are missing, and a surface without bruises is a surface that got wiped clean, over and over, by something we can't see from here. And that's the detail worth holding on to. A moon with almost no craters is a moon hiding how old it really is. Here's why that matters. Every solid body in the outer solar system sits in a shooting gallery. Comets, asteroids, stray chunks of rock, they've been raining down for over 4 billion years, and they don't miss. Look at our own moon. Its face is packed with craters, some over 3 billion years old, sitting there untouched because nothing ever came along to smooth them out. That's the normal state of things out here. Get hit, keep the scar, forever. Callisto, one of Jupiter's other big moons, is the poster child. It's so cratered, there's barely room for new ones. That surface is ancient, and it looks every bit its age. Then there's Europa. Count the craters, and you get a handful. Just a handful, on a world that has been sitting in the same storm for the same billions of years. By the math, its surface might be only 40 to 90 million years old, young enough that dinosaurs predate it. So the impacts happened. They had to. The scars just aren't there. Something has been erasing Europa's wounds, and it has not stopped. So what does the scarring? By the 1970s, telescopes on the ground had a way to ask the surface directly. Point a spectrometer at Europa, split its reflected sunlight into a spectrum, and read the dark bands where certain molecules swallow specific wavelengths. The pattern that came back was unmistakable. Water ice, and lots of it, coating nearly the whole face of the moon. Those absorption lines sit near 1.5 and 2 micrometers, a fingerprint that frozen water leaves and almost nothing else fakes. That answered one question and cracked open a bigger one. Ice is bright, ice is smooth, and ice can flow and refreeze, which fit those missing craters a little too well. But a spectrometer only reads the top layer, the first millimeters that catch the light. Everything below stayed hidden. The rock core, the thickness of the shell, whatever sat between them, None of it showed up in that spectrum. Ice on top only made scientists wonder harder about what was under it. So how far away are we actually talking? At its closest, Jupiter sits around 588 million kilometers from Earth. At its farthest, that gap swells past 968 million. Europa rides along beside it, tucked into that same enormous distance. Light is the fastest thing there is, and even light struggles to cross that void quickly. A radio signal from Earth takes roughly 35 to 52 minutes just to reach Jupiter, depending on where the two planets sit in their orbits. Send a command, and you wait. Wait for the answer, and you wait again. That round trip can stretch past an hour and a half. There's no steering a spacecraft in real time out there, no quick correction if something goes wrong. By the time you see a problem, it already happened a long while ago. No human has ever come close. No one likely will for generations. Europa is a place we can only touch through machines we build here and fling across the dark, hoping our instructions still make sense when they arrive. To learn anything real, we would have to send something there and pray it survived. And surviving isn't a metaphor here. Jupiter is wrapped in the most violent radiation environment of any planet in the solar system, a magnetic field about 20,000 times stronger than Earth's, spinning fast and trapping charged particles in belts that stretch millions of kilometers out. You can't see it. There's no warning light, no wall of fire, nothing your eyes could ever catch. It's just space, empty and black, right up until the moment it starts tearing your machine apart from the inside. Those trapped particles slam into anything that enters at a fraction of the speed of light. Electronics scramble, circuits fry. A probe crossing that region can absorb a dose in a single day that would kill a human many times over, thousands of times the lethal limit. Europa orbits right inside that killing zone. Every second it spends there, it's being bombarded, its surface soaking up a rain of energy that would sterilize anything standing on top of it. But radiation doesn't only destroy, it rearranges, and that same radiation that kills spacecraft may be quietly feeding the ocean below. So by the late 1970s, scientists had settled on a picture of Europa that felt safe. A small moon, about 3,100 kilometers across, wrapped in a shell of water ice, orbiting a giant that flooded it with radiation. Nothing about it screamed alive. The best guess was simple: a rocky core buried deep, then a thick crust of frozen water sitting on top, locked solid all the way down, cold, quiet, and unchanging for billions of years. There was no reason to expect anything else. Europa sat 671,000 kilometers from Jupiter, far from the Sun, with surface temperatures near -160 degrees Celsius. At that distance and that cold, ice just stays ice. The tidal forces we mentioned earlier hadn't been worked into the models yet, so the leading view was a dead ball, geologically finished, a museum piece frozen in place since the early solar system. It was a tidy story, and for a while it held. Everything pointed to stillness, to a world where nothing had happened in a very long time. That consensus was about to be shattered by two spacecraft passing through. By the summer of 1979, Voyager 2 was closing on Jupiter at tens of thousands of miles per hour, still weeks out, but already awake. Its cameras had been calibrated against star fields and the faces of the inner moons, tuned to catch faint light across a black gulf. The team knew Jupiter would be spectacular. The moons were a different matter. Europa sat low on almost everyone's priority list. It was the fourth Galilean moon, smaller than our own, wrapped in that bright, featureless shell. Voyager 1 had swept past months earlier and caught it only from far off, a smooth marble with a few smudges no one could resolve. So the expectations going in were modest. A cratered ice ball probably, another dead surface to catalogue and move past on the way to bigger targets. The flight plan gave Europa a closer look this time, a few 100,000 miles instead of millions, enough to finally sharpen those smudges into something. The frames started arriving line by line, building on the monitors as the distance shrank. No one at the controls was ready for what Europa's face actually looked like. Before those first sharp frames land, there are two things you need to carry with you. Two details that seem small right now, almost like footnotes, but they end up doing all the heavy lifting. Keep them close, because everything that follows leans on them. The first is the smoothness. Even from a blur, Europa refused to look battered the way every other icy world in the outer system does. No jagged rims, no shadowed pits, just a surface that seemed strangely, unsettlingly clean. The second is that faint reddish tint bleeding through the cracks. It's not the bright white you'd expect from fresh ice. Something is staining it, painting long streaks across a face that should be pale and dead. On their own, neither detail proves anything. A smooth moon could just be young, a colored surface could just be dust, but hold them side by side and they start pointing somewhere nobody wanted to go. We're going to walk right up to that answer and then stop, because you deserve to see the evidence pile up the way the scientists did. Hold on to those red lines, because they are a message written across an entire world. Here's the part that still gets me. No human being has ever looked at Europa with their own eyes. Not through a telescope in any way that matters, not from a passing ship, not once. From Earth, even the best instruments turned it into a smudge, a pale dot smeared across a photographic plate. For centuries, it was a name in a logbook and a wobble of light, nothing more. Whatever was down there, the ice, the cracks, the thing we're circling toward, stayed completely hidden. So the first real portrait was never going to come from a person leaning into an eyepiece. It was going to come from a machine, a box of cameras and circuits flung across 500 million miles, doing the looking on our behalf. We'd built a stand-in for the human eye and pointed it at the dark. And that machine kept its distance for years, coasting silent through the outer system, carrying film we hadn't developed yet. The answer was already on board. We just hadn't caught up to it. In 1979, the picture finally arrived, and it did not look like any moon we knew. Voyager 1 reached Jupiter in March of 1979, moving at roughly 39,000 miles per hour, threading past a planet 300 times the mass of Earth. It had 4 billion miles of journey behind it, and only hours to work with as the system swept past its cameras. Every target got a slot on a schedule measured in minutes. Europa didn't get much of that time. Voyager 1 passed more than 730,000 miles away, far enough that the moon stayed a smudge, a pale smear of light with no features anyone could pin down. It was a placeholder, a promise that the real look was still coming. That look came in July, when Voyager 2 swung through and closed the gap to about 128,000 miles. The cameras turned, the shutters clicked, and the data crawled back across the solar system at the speed of light, more than half an hour in transit before it ever reached a screen on Earth. Then the frames assembled, line by line, and the people watching leaned in. Whatever they expected, this wasn't it. The image that came back looked less like a moon and more like a cracked egg. Picture a pale, tan sphere, brighter than almost anything else out there, reflecting back most of the sunlight that hits it, and running across that brightness, thin, dark streaks. Some stretch for hundreds of miles, curving and overlapping, doubling back on themselves. They didn't stop at the edges of anything, no mountain ranges to break them, no deep valleys to swallow them. The lines just ran, straight through, like someone had taken a pen to a boiled egg and never lifted it. And the shell underneath them was the strange part. Smooth. Not smooth like a desert, smooth like something had wiped it clean. Across a whole world, barely a bump to be found, which is not how moons are supposed to look. Every other body they'd photographed up close wore its history on its face, craters stacked on craters, billions of years of getting hit and keeping the scars. Europa had almost none of that, just that eerie polish and those long, dark seams cutting across it in every direction. Nobody in that room could say what drew the lines, but everybody understood the shape of the problem. Lines that long do not form on solid ground. So they did the obvious thing next. They counted craters. Every airless world in the solar system keeps a record of every rock that ever hit it, punched into the surface and frozen there for billions of years. Our moon is saturated with them, thousands of scars stacked on scars, some over 3 billion years old. Callisto, another moon of Jupiter, is so battered you can barely find clean ground between the impacts. That's what an ancient surface looks like. Europa should look the same. It sits in the same neighborhood, pelted by the same debris for the same 4.5 billion years. But when scientists went looking, they found almost nothing. You can count the large craters on Europa on your fingers. That's not a small discrepancy. Fewer craters means the surface hasn't been sitting around collecting hits. Something keeps wiping the record clean, erasing the damage faster than the impacts can accumulate. And the math points somewhere uncomfortable. The face we're looking at might be only 40 to 90 million years old, younger than some rocks on Earth. A young surface means something is actively repaving Europa right now. So what actually repaves a world? On a rocky planet like Earth, we know the answer. Volcanoes flood the ground with lava, plates grind and sink, and wind and rain wear the old scars flat. But Europa has none of that machinery running. There's no air to erode anything, and it sits about 780 million kilometers from the Sun, where surface temperatures hover near -160 degrees Celsius. At that cold, water ice behaves like solid rock. It shouldn't flow, it shouldn't melt, and it definitely shouldn't heal itself. You could try to explain it with ice volcanoes, slushy eruptions pushing up from below, but that needs a warm interior. You could imagine the whole crust slowly churning like taffy, except that needs heat too. Every option lands on the same impossible requirement. Something down there has to be warm enough to keep the ice soft and moving on a moon that should have frozen solid billions of years ago, and yet the craters keep disappearing. The only thing that erases craters that fast is a surface that moves. Look closer at those cracks, and you notice something the white ice can't explain. The long fractures aren't clean. They're stained a dirty reddish brown, running for hundreds of miles like veins across the whole moon. Scientists call these features lineae, and the color sits right along the widest, most disturbed cracks, the ones that look like they've split and healed and split again. Pure water ice is bright and neutral. It doesn't turn that shade on its own. When the spectrometers looked at the light coming back, the reddish tint lined up with salts, not table salt exactly, but salty compounds, the kind you'd get from mineral-rich water. And the fresher the crack, the stronger the color, as if whatever painted those lines had come up recently and hadn't faded yet. Something is being delivered to the surface along those fractures, from a source we haven't accounted for. We'll get to what could dissolve salts like that. For now, hold on to the color itself, because it's telling you where to look. Red usually means chemistry, and chemistry here means something is leaking out. So step back for a second and look at what we've got. A shell that resurfaced itself. Cracks that stretch for thousands of kilometers. Streaks of red where something salty pushed up through the ice. On their own, each one is a puzzle you could shrug off. Together, they start whispering the same thing. Every clue on that surface behaves like a symptom, not a cause. Something down there is moving, leaking, rewriting the crust from below. The ice isn't the story. The ice is the lid. That's the suspicion scientists couldn't shake. Not a proof yet, nothing you could hold up and defend, just a pattern that kept refusing to go away. If the surface is this young, this cracked, this stained, then maybe it's floating on something that flows. And once that idea gets in your head, you can't unsee it. You look at Europa, and you stop seeing a frozen ball. You start seeing a surface that's hiding what it sits on. Every crack, every color, every smooth plane was pointing downward. So here's the question that changes everything. What keeps that surface moving if the sun barely reaches out this far? At Jupiter's distance, sunlight is about 25 times weaker than it is at Earth, so solar heat isn't the answer. Something else has to be doing the work. That something is Jupiter itself. The planet is 318 times more massive than Earth, and its gravity doesn't just hold Europa in place. It pulls on the near side harder than the far side, stretching the whole moon along the line between them. Now watch what happens as Europa orbits. Its path isn't a perfect circle, so the distance to Jupiter keeps shifting, and the pull rises and falls with every lap. The moon gets stretched, then relaxes, then stretched again, over and over. Bend a paperclip back and forth and feel the metal warm up under your fingers. Flexing creates heat. Do that to an entire moon, on a cycle that never stops. And you're not talking about a little warmth. You're talking about heat generated deep inside, far from any sunlight. If Jupiter is squeezing Europa like a stress ball, that energy has to go somewhere. So why doesn't the squeezing ever stop? Because Europa's orbit isn't a perfect circle. It's slightly stretched, an ellipse, which means the moon's distance from Jupiter keeps changing as it goes around. When Europa swings closer, Jupiter's gravity yanks harder and the moon bulges. When it drifts farther out, that grip eases and the bulge relaxes. Rise, fall, on a loop that's been running for billions of years with no off switch. And here's what keeps that stretch locked in. Io, the neighbor closer in, tugs on Europa at regular intervals, nudging its orbit so it can never settle into a tidy circle. The elongation gets refreshed before it can fade. So the interior never gets to rest. The whole moon is flexed and released, like a wire you bend back and forth in your hands until you can feel it warming at the crease. Do that to rock and ice on a planetary scale, without pause, and the friction adds up. Constant kneading generates heat, and heat is the enemy of ice. If that sounds like theory, look one moon closer to Jupiter. Io sits inside the same gravitational tug-of-war, squeezed by the giant on one side and the outer moons on the other. And Io doesn't just warm at the creases, it burns. When Voyager 1 flew past in 1979, engineer Linda Morabito spotted a faint plume rising 300 kilometers off the edge of the disk. It was an eruption, caught mid-launch, throwing material higher than any volcano on Earth ever could. Io turned out to be the most volcanically active body in the solar system, with over 400 active volcanoes resurfacing it in real time. Nothing on Io is old. Lava lakes glow, sulfur paints the ground yellow and red, and the whole surface gets repaved faster than craters can form. All of that heat comes from the same flexing we just described, tides kneading the interior until the rock melts. So the mechanism isn't a guess anymore. We have a working example right next door, running hot enough to melt stone. If tides can set Io on fire, imagine what a gentler dose does to a ball of ice. So run the numbers on Europa. The surface sits around -160 degrees Celsius, cold enough that the ice is hard as rock. But heat doesn't stay at the surface. Squeeze the moon over and over, and the warmth builds where the flexing is strongest. Deep down, far below anything you could see from orbit. Follow that heat downward, and you hit a line. Somewhere maybe 10 to 20 kilometers beneath the crust, the temperature crosses the point where solid ice can't hold anymore. Below that line, water. Above it, a frozen shell riding on top. And if that line is real, the math gets strange fast. A global layer of liquid water, maybe 60 to 100 kilometers deep, wrapped around the whole moon. That's more water than every ocean on Earth combined, tucked under a lid of ice on a world smaller than our own moon. But notice what we just did. We took a temperature, a depth, and a mechanism, and we drew an ocean out of thin air. No one had seen it. No probe had touched it. On paper, the ocean should exist, but paper is not proof. And plenty of scientists weren't buying it. The math worked, sure, but math can describe a lot of things that never actually happen. A group of researchers looked at the same tidal heating numbers and drew a very different picture. Their argument went like this. The heat from Jupiter might warm the interior just enough to keep the deep ice soft, slowly churning, but still frozen solid all the way down. Warm ice can creep and flow like glacier ice on Earth, no liquid required. In that version of Europa, there's no ocean at all, just kilometers of ice, cold near the surface, warmer and mushier at the bottom, deforming over millions of years without ever melting through. The cracks and the smooth planes could come from moving ice, not moving water. Both camps were staring at the exact same photographs. Same fractures, same faint discoloration, same missing craters. One side saw a hidden sea, the other saw a frozen shell that only looked alive. There was no clean way to choose between them from 100 million kilometers away. The only way to settle the argument was to look inside a world we could not drill. Here's the problem with everything Voyager gave us. It never stopped. Both probes came screaming through the Jupiter system in 1979, snapped what they could, and kept going toward the edge of the solar system. Europa got minutes of attention, not months. Voyager 2 made the closest pass, and even then it stayed around 205,000 kilometers out. From that distance, the sharpest images resolved features maybe 2 kilometers across. You could see the cracks, you could not see what filled them. So the pictures raised more questions than they answered. How thick was the ice? Was there liquid underneath, or just warmer, softer ice pretending? Why did the surface look so young when everything around it was scarred by billions of years of impacts? A flyby is a glance. It catches a moment and carries the mystery away with it. To answer any of this, you couldn't just pass by and wonder. You needed to loop back, again and again, and watch how the moon changed. To go deeper, we needed a spacecraft that would stay. But that spacecraft was still years away. Voyager had gone quiet, its cameras pointed at colder, farther targets, and Europa was left in a strange kind of limbo. For a while, the moon didn't live in photographs at all. It lived on chalkboards and in printouts, in the back and forth of people who couldn't agree on what they'd already seen. So the work moved into equations. Researchers modeled how much heat Jupiter's pull could pump into a body that size, how thick a shell of ice might sit on top, how long it could stay warm. Every answer depended on a number nobody had measured yet, so the arguments kept circling back on themselves. Years passed like that. A generation of grad students grew up on a moon they'd only met through 1979 flyby data and a stack of competing theories. The images were too blurry to settle anything, and the funding for a return trip came slowly, if it came at all. What finally broke the stalemate wasn't a sharper guess. It was a plan to stop guessing. The next spacecraft would not just fly past, it would circle Jupiter for years. So when the images finally came back sharp, the first thing anyone noticed was the lines. Long, dark streaks running for hundreds of miles, some straight, some gently curved, crossing each other like scratches on frosted glass. Scientists called them lineae, and at first they looked random. They weren't. When researchers traced the older cracks and compared them to fresh ones, the pattern had shifted. Each new set of fractures pointed a few degrees off from the last, as if the whole surface had slowly turned since the older ones formed. Here's what that turning implies. Europa is locked to Jupiter, one face always leading, so the tides that pull the shell apart should always crack it in the same directions. But the cracks don't line up with where they should be. They line up with where the shell used to be. That only works if the outer crust isn't bolted to the rock below. Something has to let it slip, rotate, drift a little faster than the core it's wrapped around. A rigid shell over solid ground can't do that. Cracks that curve like that only appear when the surface floats. So picture the crust doing what no solid crust should. Not fixed to the rock below, not bolted to a foundation, but resting on something slick enough to let the whole outer layer glide. The ice becomes a shell, wrapped around the moon like a peel that isn't quite stuck to the fruit. And a shell that floats can turn. It can rotate a hair faster than the interior, slide over the deeper mass, and carry every crack along with it as it goes. That's the motion those curving fractures were quietly recording, a surface in slow, patient drift. It's a strange thing to sit with. The ground you'd stand on wouldn't be ground at all. It would be a lid, kilometers thick, gliding above whatever holds it up, free to shift by degrees over thousands of years. But an idea like that comes with a debt it has to pay. You can draw the shell, you can trace the drift, you can watch the cracks bend exactly the way they should. A floating shell needs an ocean to float on, and no one had found one yet. So the search moved to the surface itself, and it found something that doesn't sit easily. Scattered across Europa are patches where the smooth, cracked terrain just stops. Inside those patches, the ice looks wrong, like someone took a frozen landscape, broke it into pieces, and let it set again before the pieces could drift back into place. Scientists call these regions chaos terrain, and the name is honest. Blocks the size of city districts sit tilted at odd angles. Some have rotated, some have slid. A few look like they've been shoved up and refrozen at a slightly different height than the ground around them, as if the whole neighborhood was briefly loose. Picture a pond in early spring when the top layer starts to give. The sheet fractures into slabs, they jostle, they turn, and then a cold night locks them back down in a jumbled mess. That's what these areas look like from orbit, except the slabs are miles across and the pond is a moon. And that comparison carries a quiet problem you can't shake once you've seen it. Ground that looks like shattered pack ice is ground that once had water beneath it. Look closer at those slabs and something stranger shows up. Some of them aren't sitting square, they've turned. You can trace the old crack patterns from one block to its neighbor and watch them fail to line up, like puzzle pieces someone twisted before the glue set. A few blocks look tilted, one edge riding higher than the other. Others have clearly slid sideways from where they started, leaving a matching gap behind them. Match the fracture lines back together in a photo, and you can rebuild the original surface, then watch it come apart in slow motion. That only happens one way. Solid ground doesn't rotate. For a block miles across to spin and drift and settle at a new angle, whatever it was resting on had to give. Something under it had to move, carry it, and let it go somewhere else. And then it stopped. The blocks are frozen exactly mid-motion, caught halfway through a journey, welded back into place by cold that never lets up. Something let those blocks move, and then sealed them back in. So let's line up what we've got. The cracks run for thousands of kilometers, curving in ways that match a shell riding on something that flexes. Straight lines don't bend like that unless the ground beneath them is moving. Then there's the smoothness. Europa's surface has almost no big craters, which means it keeps repaving itself, wiping the record clean every few tens of millions of years. Only something soft and mobile underneath does that. Add the chaos terrain, those shattered blocks frozen mid-drift. Add the reddish stains bleeding along the fractures, colors that hint at salts carried up from below. Point by point, every clue leans the same direction. Liquid. Somewhere down there, liquid. But lean isn't proof. A crack can be explained away. A color can have three boring causes. Circumstantial evidence stacks tall, and it still isn't a confession. You can build a case this good, and a skeptic can still walk, because nobody had actually touched the thing that would settle it. The jury needed a smoking gun, and one spacecraft was about to fire it. So what do you send to interrogate a world sealed under miles of ice? You can't drill from orbit. You can't peel back the crust. Every answer has to come from a distance, filtered through instruments that read what your eyes never could. Picture the payload, cameras sharp enough to map cracks a few meters wide, spectrometers to taste the chemistry baked onto the surface, radar tuned to punch down through frozen layers and listen for whatever bounces back. But the instrument that matters most here doesn't take pictures at all. It's a magnetometer, mounted far out on a boom to keep the spacecraft's own electronics from drowning out the signal. Its whole job is to feel fields that are completely invisible, the kind you can't photograph, can't touch, can't point at. And that's the strange part. To confirm an ocean nobody can see, you don't go looking for water, you go looking for a magnetic whisper, a bend in a field, something salt would leave behind. A magnetometer cannot see water, but it can feel salt, and that changes everything. So here's the physics that makes the whole trick work. Pure water is a terrible conductor. Add salt and everything changes. Dissolve sodium and chloride into it, and those ions start carrying charge, turning ordinary seawater into a fluid that electricity moves through easily. Now put that salty layer near Jupiter. The planet spins fast, once every 10 hours, and it drags a monstrous magnetic field around with it. Europa sits inside that field, and because Jupiter is tilted, the field the Moon feels keeps shifting, sweeping back and forth as the giant rotates. A changing magnetic field near a conductor does something specific. It stirs up electric currents inside that conductor. Those currents then throw off a magnetic field of their own, a faint echo pushing back against the one that caused it. Salty water buried under the ice would do exactly this. That echo is the fingerprint. Solid rock won't produce it. Frozen ice won't either. Only a global layer of conducting liquid would answer Jupiter's pulse with a pulse of its own. If a hidden ocean existed, it would betray itself the moment Jupiter's field swept past. So the plan came down to geometry and timing. Bring the orbiter in low, drop it into the region where Jupiter's field is strongest, and let the magnetometer listen for a reply. If Europa was hiding salt water, this was where it would answer. The trouble is you don't get to linger. A flyby is a slingshot, not a hover. The spacecraft crosses the whole close approach window in minutes, sometimes screaming past at more than 6 kilometers per second, and the instruments have to catch the signal on the way through. Every pass had to be aimed like a rifle shot. Wrong angle, wrong altitude, wrong moment in Jupiter's spinning field, and the reading would smear into noise. Teams argued over trajectories, because you only get so many chances before the fuel and the mission clock run out. And then the day arrives. The orbiter tips toward the ice, the field builds around it, and the magnetometer starts sampling faster than anyone can read it live. Somewhere in those numbers is either an ordinary dead moon or something none of us expected. This is the moment the cold open came from, and now we know why the needle moved. To understand where that needle came from, back up to 1995. That December, after a 6-year cruise across 500 million miles, NASA's Galileo fired its main engine and let Jupiter's gravity catch it. For the first time, a spacecraft wasn't just flying past the giant planet, it was moving in. Everything before Galileo had been a glance. Voyager screamed through the Jupiter system in days and grabbed what it could on the way out. Galileo settled into a long, looping orbit that would swing it back around again and again for nearly 8 years, using each pass of a moon to bend its path toward the next. That patience changed the whole game. Instead of one blurry snapshot of Europa, Galileo could return, tighten its aim, and come back lower the next time. It carried a camera, a magnetometer, instruments built to taste the space around it, and years of fuel to keep the tour going. Io, Ganymede, Callisto, Europa, one careful loop at a time. For the first time we would linger over Europa long enough to interrogate it. Galileo didn't just glance at Europa. It came back, again and again, dropping to within 400 kilometers of the surface on some passes, closer than a lot of satellites orbiting our own planet. Each approach was scheduled months in advance, the trajectory bent by Jupiter's gravity into a slingshot that flung the craft toward the moon and back out again. The problem was the radiation. Jupiter is wrapped in belts of charged particles moving at nearly the speed of light, and every time Galileo dipped inside them, it absorbed a dose that would kill a human in minutes. The electronics took hits too. Memory glitched, systems tripped into safe mode, and engineers held their breath through each close pass. So the flybys were fast. The instruments had a narrow window, sometimes just minutes near closest approach, to sweep the surface, sample the field, and record everything before the craft climbed back out to safety. 12 times Galileo threaded that gauntlet, each run grabbing a little more of the picture. One of those passes captured the reading that reopens our cold open. Here's what the magnetometer saw as Galileo swung past. Jupiter throws out a monster magnetic field, and it doesn't sit still. As Europa orbits, that field around it flips direction on a rhythm, sloshing back and forth every 11 hours or so. And Europa answered. Every time Jupiter's field pushed one way, a second field pushed back from the moon, weaker, delayed, pointed the opposite direction. The needle didn't just twitch randomly, it bent in a pattern, and the pattern tracked Jupiter's rhythm almost perfectly. That's the signature of an induced field. You get it when a changing magnetic field passes through something that conducts electricity, driving currents that generate a field of their own. Iron cores don't do this. Solid rock doesn't do this. A cold ball of pure ice doesn't do this. But a global shell of salty, briny liquid would do exactly this. And the numbers Galileo pulled matched that case with unsettling precision. The field was not from the moon itself, which meant something conductive was hiding inside. Here's what made the signal so hard to explain away. Jupiter's magnetic field isn't aligned with its spin axis. It's tilted by about 10 degrees. So as the planet rotates every 10 hours, the field at Europa's location doesn't stay put. It sweeps back and forth like a searchlight passing over the moon. And Europa's response tracked that motion. The induced field grew and faded and flipped in rhythm with Jupiter turning underneath it. Whatever was answering the call had to be responding to the changing field around it, in real time, on Jupiter's clock. That behavior points to a specific culprit. You need a layer that conducts electricity, wrapped around the whole moon, close enough to the surface to react this strongly. Solid rock deep in the interior can't switch fast enough. Pure ice barely conducts at all. Galileo couldn't drill. It couldn't see through the crust. It just watched a needle twitch in step with a giant planet and let the physics narrow the options down, one by one, until almost nothing was left standing. Only a shell of salt water could produce a signal that danced with Jupiter. So put it together. A magnetic field that isn't Europa's own, but a borrowed one, switched on by Jupiter and switching off in perfect time. A response that only makes sense if something conductive is wrapped around the whole moon, close beneath the surface, moving freely enough to carry current. Ice doesn't do that. Rock doesn't do that. Salt water does. Not a frozen crust with a few damp cracks, but a genuine ocean, liquid, global, and briny enough to conduct like the seas back home. That's the verdict the physics keeps returning. After every flyby, every twitch of that needle, the least strange explanation left standing is the strangest thing to say out loud. There is an ocean under the ice of another world, and it wraps the entire moon. We're not talking about a puddle or a hidden lake. We're talking about a sea buried under a shell, dark, ancient, and untouched by sunlight, sealed in for who knows how long. And here's the part that keeps me up. Confirming water was the easy part, and it was only the beginning of the fear. So how deep are we going? The ice shell up top runs somewhere between 15 and 25 kilometers thick, and that's the conservative read. Some models push it thinner in spots, but even the thin estimates bury you under kilometers of solid, cracked ice before you'd ever touch liquid. Now punch through that crust. Below it, the ocean itself is estimated at 60 to 150 kilometers deep. Take a second with that number. Earth's deepest trench, the Mariana, bottoms out around 11 kilometers. Europa's ocean could be 10 times deeper than the deepest place on our entire planet. And Europa is a small moon, smaller than ours. Yet crunch the volume, and this one buried sea holds roughly 2 to 3 times more liquid water than every ocean on Earth combined. All of it stacked inside a world you could tuck neatly inside the Pacific. So picture that column again. Kilometers of ice, then a black sea, deeper than anything we've mapped, pressing down in total darkness. An ocean that deep has a floor, and the floor is where things get interesting. Let's do the math on that ocean, because the number doesn't feel real until you sit with it. Europa is small, about 3,100 kilometers across, smaller than our own moon. You could tuck it inside the width of the continental United States and still have room to spare. And yet, under that ice, estimates put the water at roughly 2 to 3 times the volume of every ocean on Earth combined. Every sea, every trench, every drop of the Pacific and Atlantic and Arctic, doubled, maybe tripled, and then sealed inside a moon you could drive across in a day. That's the part that bends your head. All of Earth's water spreads across a planet 12,700 kilometers wide, a thin skin over a huge sphere. Europa takes more than that and stacks it into a single deep shell, wrapped tight, hidden under kilometers of frozen crust. So the scariest thing about Europa isn't the cold or the dark or the distance, more water than Earth in a place we assumed was dead, and the water is only the setup. Pure water can't hold together an ocean this active, so the question becomes, what's dissolved in it? Galileo's near-infrared readings picked up something on the surface that wasn't clean ice. The spectra were smeared, distorted, bent away from what frozen water alone should look like. The best matches came from hydrated salts, magnesium sulfate and sodium chloride, the same kind of table salt sitting in your kitchen. Later work with Hubble tied that yellowish surface color to sodium chloride, altered by radiation. That salt didn't fall from space. It welled up from below, dragged out of the water, and left behind on the ice. Then there's the other direction. Jupiter bombards Europa with radiation that cooks the surface and creates oxidants, compounds hungry to react. Cycle the crust slowly enough, and some of that gets folded back down into the sea. So the ocean isn't just salty. It may sit between acids and oxidants delivered from above and minerals leached from the rock below, a chemistry stirred from both ends. And the exact mix of salts hints at reactions we usually only see where life feeds. But before we ask what's living down there, we have to answer a nastier question. How thick is the lid? Because the ice shell isn't just a wall between us and the water. It's the whole reason this argument won't die. One camp reads the surface and sees a thick shell, maybe 20 to 30 kilometers of solid ice. They point to the big domes and pits, features you'd expect from warm ice rising slowly, like blobs in a lava lamp, never quite breaking through. In that model, the ocean is sealed off, locked far below, cut off from the sky. The other camp looks at the cracks and the chaos terrain, those shattered zones that look like sea ice that broke, drifted, and refroze. They argue the shell could be just a few km thick, thin enough for the ocean to nearly touch the top. Same moon, same photos, two answers that couldn't be further apart. And nobody has drilled through to settle it. The debate is still open, right now, unresolved. If the ice is thin, then whatever is below can reach the surface, and be reached. Look at the surface long enough, and you start to notice the scars. Wide, dark patches where the smooth ice breaks into a jumble of blocks, like a frozen lake that cracked, shifted, and refroze at odd angles. Scientists call this chaos terrain, and it covers huge stretches of Europa. The best explanation is unsettling. Warm ice, softer and less dense than the crust around it, rises in slow columns from deep in the shell. It pushes up like wax in a lamp, cracking the surface above it, dragging material along for the ride. In some places, that rising material may not stop at ice. Pockets of liquid water could migrate upward, refreezing near the top and leaving telltale domes and pits behind. The shell isn't a sealed lid. It churns, slowly, over thousands of years, trading material between the ocean below and the vacuum above. And that's the part that changes everything. If the shell moves, then the ocean isn't locked away forever. Whatever is down there can be carried up, delivered to a surface we can actually see. Anything dissolved in that ocean could be riding those plumes toward the sky. So think about what that means for a second. If material moves from the seafloor all the way up through the ice, then the bottom of that ocean isn't some sealed dead zone. It's connected. And the bottom is exactly where things get uncomfortable. Because we already know what Europa's floor probably looks like. A rocky seabed, pressed under 100 kilometers of water, warmed from below, with mineral-rich fluid seeping up through cracks in the rock. No sunlight ever reaches it. It has never seen a single photon from the sun. And here's what should stop you cold. Those same conditions, dark water, hot rock, dissolved minerals, and chemistry doing the work that light usually does, aren't hypothetical. We're not guessing at whether nature can build something in a place like that. We know it can, because it already did. Roughly 4 billion years ago, some of the earliest life on our own planet may have started in an environment that matches Europa's seafloor almost point for point. There is one place on Earth just like Europa's seafloor, and life there thrives in the dark. So picture the bottom of that ocean. On some worlds, water freezes solid all the way down, and you get a boring sandwich of ice on ice, with no place for chemistry to happen. Europa almost certainly doesn't work that way. The models point to a rocky floor, a genuine seabed made of silicate mantle sitting under 100+ kilometers of liquid water. That single detail changes everything. Rock isn't just something to sink to. Rock is a pantry. When liquid water presses against warm mineral rock, it doesn't just sit there. It leaches. It pulls iron, sulfur, magnesium, and phosphorus straight out of the stone and carries them into the water above. Ice can't do that. Ice offers nothing to eat. That's the difference between a sealed freezer and a kitchen. A frozen core gives you a dead, closed system. A rocky one gives you contact, and contact gives you ingredients. The ocean isn't floating on more of itself. It's leaning on a chemistry set. And we're holding back exactly what that set can make, because the reactions matter more than the ingredients. Water touching hot rock is a recipe, and we have tasted what it cooks. So where does the heat come from? Europa sits 485 million miles from the sun, so sunlight barely warms its surface past 260 degrees Fahrenheit below zero. Nothing that faint keeps an ocean liquid for billions of years. The answer is closer to home, and it comes from Jupiter itself. As Europa loops around the planet, its slightly stretched orbit lets Jupiter's gravity squeeze and release it on every pass. The moon flexes over and over, and that constant kneading generates friction deep inside. Friction makes heat. It's the same reason a paperclip warms up when you bend it back and forth. For a long time, this tidal heating was just a good idea on paper. Now the ocean is the receipt. A body of water that has stayed liquid under a frozen crust for eons is proof that something has been feeding it warmth the whole time, quietly, without a break. And here's what makes that unsettling. Tidal flexing doesn't stop at the ice. It works the entire moon, all the way down. If the tides reach all the way to the core, the floor of that ocean could be on fire. But heat alone doesn't make life. Every living thing we know of runs on energy. Some current it can tap to build itself and fight off decay. On Earth, that current almost always traces back to one place: the sun. Sunlight hits the surface, plants convert it, and the whole food chain climbs up from there. Take the light away, and in most places, everything downstream starves. So the first question anyone asks about Europa is simple: where does the light go? It doesn't get far. Europa sits over 5 times farther from the sun than we do, so the light arriving is already faint. Then it hits kilometers of solid ice. Photons don't punch through that. A few meters down, the ocean is in total, permanent darkness, and it stays that way all the way to the floor. So if anything is living in that water, it can't be running on sunlight. Something else has to be feeding it, some other current running through the black. That should be the end of the story. Life without sunlight sounds impossible, until you remember where we found it first. By 2003, Galileo was running on fumes. It had orbited Jupiter for 8 years, survived radiation doses that would have killed a human hundreds of times over, and its instruments were failing one by one. The fuel that let it steer was almost gone, and once that ran out, the spacecraft would drift, uncontrolled, through a system it had mapped in stunning detail. That was the problem. A dead, tumbling probe eventually crashes into something, and the something everyone worried about was Europa. Galileo had flown out of Earth's biosphere, carrying whatever hardy microbes survived launch, and those hitchhikers might still be viable, frozen in the machine's shadows. So on September 21, 2003, NASA sent one last command. Galileo dove straight into Jupiter's atmosphere at about 108,000 miles per hour and burned away in seconds, scattering into a planet that could never host what it might have carried. They didn't have to do that. They chose to, because of what they'd started to suspect was waiting under Europa's ice. We destroyed our own spacecraft to keep Europa clean, and that decision says everything. There's a rulebook for this. It's called planetary protection, and it's older than most people realize, written into international law back in 1967 under the Outer Space Treaty. Every nation that signs agrees to the same thing. Don't contaminate other worlds with life from ours. NASA takes it seriously enough to have an entire office for it. Spacecraft headed to sensitive places get baked in ovens, scrubbed in clean rooms, assembled by technicians in full-body suits. The goal is to strip away Earth microbes before launch, because a single hardy bacterium can survive years in the vacuum of space and wake up when it finds water. And Europa has water, oceans of it, right under the ice. So Europa sits in the highest protection category we have, the same tier we reserve for the handful of places where contamination could ruin everything. Think about what that means. We're not protecting the rock, we're protecting the chemistry, the possibility, the answer to a question we haven't been allowed to ask yet. You only quarantine a place you think might already be inhabited. So here's the problem with a buried ocean. It sits under 15 to 25 kilometers of ice, and no probe we've built could drill through that in a single mission. To read the water, we'd have to reach a moon 628 million kilometers away, land, melt down through solid crust, and survive whatever's waiting. That's decades of engineering we don't have yet. So astronomers tried the opposite direction. Instead of going down into Europa, they watched from above, hoping the ocean might come to them. If any water escaped through the shell, even a trace, it would carry the chemistry of that hidden sea up where a telescope could see it. That's where Hubble comes in. It orbits 540 kilometers above Earth, and it was never built to study a moon of Jupiter in detail. But it can catch faint ultraviolet light, the kind hydrogen and oxygen give off when they're torn apart by Jupiter's radiation. So they pointed it at Europa's edge, the thin line where the moon's curve meets black space, and they waited. If anything was leaking out, that's where it would show. In 2013, Hubble caught something rising off Europa's edge. What Hubble saw was faint, a smudge of hydrogen and oxygen near the South Pole, the chemical fingerprint of water broken apart by sunlight. The signal sat at the edge of what the telescope could even detect, right at the noise floor. But the numbers, if you took them seriously, were staggering. Columns of vapor rising roughly 200 kilometers above the surface, taller than the moon's own crust is thick. That's water leaving Europa and arcing back down like a fountain in slow motion. Then it got complicated. Follow-up looks came back empty. Other teams pointed the same instruments at the same spot and saw nothing at all, which is exactly what you'd expect if the plumes flicker on and off, and also exactly what you'd expect if the first detection was a ghost in the data. So the honest answer is we're not sure. The plumes might erupt on a schedule tied to Europa's orbit, when the moon flexes and cracks open. They might not be there at all. But if they are real, the implication rearranges everything. If those plumes are real, we can sample the ocean without ever landing. But here's where the hope runs into a wall. Those plumes have never been easy to see. When Hubble first spotted them in 2012, it caught faint smudges of hydrogen and oxygen near Europa's South Pole, and then, when it looked again, they were gone. Later attempts found nothing. Some searches turned up a hint, others came back empty, and the signal was always weak, right at the edge of what the instrument could measure. If they erupt at all, they seem to come and go, not the steady geysers you might picture. That inconsistency breeds real doubt. A few researchers have argued the detections could be noise or quirks in how the data was processed, ghosts in the numbers rather than water in the sky. Nobody has watched a Europan plume erupt in real time and confirmed it beyond argument. So the picture stays split. On one side, tantalizing evidence that the ocean might be venting into space. On the other, a nagging suspicion that we're seeing what we want to see. Faint or not, the mere possibility rewrote how we would explore Europa. So let's leave Europa for a minute and drop straight down into our own ocean. Go deep enough, past 2,000 meters, and sunlight quits entirely. No photosynthesis, no plants, no green anything, just cold black water and crushing pressure that would flatten a submarine hull. Then, in 1977, a research sub called Alvin was creeping along the Galapagos Rift when the crew saw something that made no sense. Chimneys of rock spewing water at 350 degrees Celsius into that frozen dark, and clustered around them, life. Not a few stragglers, whole cities of it. Tube worms taller than a person, swaying in the current, ghost white crabs, mats of bacteria, clams the size of dinner plates, an oasis blooming where every textbook said nothing should survive. The trick is what's feeding them. These vents leak chemicals up from the crust, hydrogen sulfide, methane, dissolved metals. Microbes crack those molecules open for energy, and everything else eats the microbes. It's a whole food web, wired to the planet's interior instead of the sky. The creatures around those vents never see the sun and never needed to. That process has a name: chemosynthesis. Instead of pulling energy from sunlight the way plants do, these organisms pull it straight out of chemistry, from the minerals and heat leaking up through the seafloor. We didn't even know it was possible until 1977, when a submersible called Alvin dropped into the dark near the Galapagos Rift. The scientists expected barren rock. What they found were tube worms 2 meters long, clams the size of dinner plates, whole colonies crowded around cracks in the crust, thriving in total blackness under crushing pressure. No light reached them. None ever had. The entire community ran on hydrogen sulfide bubbling up from below, a compound that would poison most life on the surface. So the rule we assumed was universal, that life needs the sun, turned out to be a local habit. Down there it just needs liquid water, a chemical gradient, and heat to drive the reactions. And that's the moment Europa's ocean stops feeling like an empty tank of water buried under ice. Because everything those Earth ecosystems need, Europa might quietly have too. So let's run the checklist. Life, as far as we know it, needs 4 things, and we can start ticking them off one at a time. Water first. Europa's global ocean holds an estimated 2 to 3 times more liquid water than every ocean on Earth combined, sealed under the ice for billions of years. Energy, second. The same tidal flexing that keeps that ocean from freezing also feeds heat into the rock below, and where warm rock meets cold water, you get exactly the kind of chemical push that living things run on. Chemistry, third. The salts and compounds smeared across the surface suggest the ocean is loaded with the raw ingredients, sulfur, carbon, the building blocks that reactions need to actually go somewhere. Then there's time. Earth took hundreds of millions of years to turn chemistry into biology, and Europa has been sitting in the dark with a warm, salty ocean for roughly 4 billion. That's not a quick experiment. That's a slow one that's had every chance to finish. Water, energy, chemistry, time. Europa checks nearly every box we thought only Earth could check. But there's one box we haven't looked at yet, and it starts at the surface. Jupiter throws a brutal amount of radiation at Europa. Charged particles slam into that ice shell at a dose that would kill a human standing there in minutes. Here's what that radiation does to the ice. It breaks water molecules apart and rebuilds them into oxidants, things like hydrogen peroxide and molecular oxygen. The surface of Europa is quietly manufacturing the very chemicals that life on Earth breathes. And that changes the math. Most ecosystems need something to burn and something to burn it with. Europa's ocean might have the fuel from below, from the rock, and now the surface is cooking up the other half up top. But there's a catch that keeps this from being a clean answer. Those oxidants are stuck on the outside, and the ocean is buried under kilometers of ice. Nobody's confirmed the two ever actually meet. So the whole idea hangs on one unproven step. The radiation trying to kill us might be delivering fuel straight to the deep. Here's the part that keeps scientists up at night. That ocean isn't young. Models of Europa's core and tidal heating suggest the water has been down there for something like 4 billion years, roughly as long as Earth has had oceans of its own. Think about what that number actually means. Chemistry doesn't need to happen fast. It needs to happen slowly, over and over, across an unimaginable stretch of time. Give simple molecules enough cycles, enough heat, enough contact with rock, and the reactions start building on themselves. On Earth, that same runway is exactly how the line between chemistry and biology got blurry. Molecules learned to copy themselves. Copies started competing. Nobody knows the precise moment it crossed over, only that it did. In water, not so different from the one hiding under that ice. So Europa has had the ingredients, the energy, and the one thing that turns maybe into eventually, time. Whether that dark ocean ever took the same step, we genuinely can't say yet. But on Earth, that much time and that much water only had one outcome. So put the pieces on the table together. A saltwater ocean, twice the volume of every sea on Earth, sealed under a shell of ice for billions of years. That's the foundation, and by itself it already outclasses almost anything else in the solar system. Then stack the rest on top. Heat, pumped in by Jupiter's tides, keeping that water liquid without a single ray of sunlight. A rocky floor that can leak minerals and energy the same way our own hydrothermal vents do. Carbon, hydrogen, oxygen, nitrogen. The raw chemistry that every living thing we know is built from. Line those clues up side by side and the pattern looks familiar, because we've seen life bootstrap itself from far less right here at home. Every box that mattered on early Earth, Europa seems to check. And still, the honest word is could, not does, not is. A place can hold every ingredient and stay empty, and we have zero direct evidence anything down there is alive. Building the case was one thing. Testing it required a mission built for exactly this. So NASA built one. Europa Clipper, the largest spacecraft the agency has ever made for a planetary mission, stretches over 30 meters tip to tip once its solar arrays unfold. Those wings are that big for a reason. Out by Jupiter, sunlight is roughly 25 times weaker than it is here, so it needs every square meter it can get just to stay powered. Its whole job is one question. Not whether Europa has life, but whether Europa could support it. Habitability, not detection. The team behind it spent years narrowing that goal down, because a spacecraft can only carry so much, and every kilogram had to earn its place. It won't land, it won't drill. Instead, it'll loop through the Jupiter system and swing past Europa again and again, reading the moon from above with a suite of instruments tuned to look for water, chemistry, and heat. Each pass gathers a little more of the picture we've been building this whole time. And it's real. It's assembled, tested, and already gone. It launched in 2024, and it will not arrive for years. So here's the puzzle Clipper has to solve. To study Europa up close, you'd think you'd just park a spacecraft in orbit around it and start collecting data. But Europa sits inside one of the most violent radiation zones in the solar system, fed by Jupiter's monstrous magnetic field. That radiation isn't a minor nuisance, it's a shredder, tearing through electronics and cooking sensitive instruments. So the engineers pulled a trick. Instead of orbiting Europa, Clipper orbits Jupiter itself, looping out wide into calmer space, then swinging back in for a fast, close pass. They call them flybys. Nearly 50 of them are planned, some skimming as low as 16 miles above the ice. Each pass is a quick raid. Dip in, grab everything the instruments can, then retreat back out before the radiation dose climbs too high. It's a spacecraft built to run, gather, and run again, dozens of times over. And that careful choreography exists for one brutal reason. It cannot orbit Europa directly, because the radiation would fry it in weeks. So what's packed into this thing during those fast flybys? Clipper carries 9 instruments, and they're tuned to work fast, grabbing data in the minutes it takes to scream past the surface. Each one answers a different question about what's hidden down there. There's an ice-penetrating radar that sends signals down through the crust, listening for echoes that reveal how thick the shell is and whether pockets of water hide inside it. There are cameras sharp enough to map the surface down to features the size of a car, tracing every crack and ridge across that frozen shell. A magnetometer reads the moon's magnetic field, which can quietly betray the salty ocean sloshing underneath. Thermal instruments hunt for warm spots, places where the ice might be thin or recently cracked open. Together, they build a portrait of a world we've only ever glimpsed from far away. And then there are the instruments that don't just look, they taste. CLIPR carries a mass spectrometer and a dust analyzer, tools designed to sample tiny particles floating above the surface and read their chemistry molecule by molecule. One of those instruments is built to catch the ocean in the act of escaping. But tasting what escapes only tells you so much. The real question sits underneath, locked away where no camera can reach. How thick is the shell? Is it a few kilometers of ice or dozens? That's where the radar comes in. CLIPR carries an instrument called reason, and it does something almost eerie. It fires radio waves straight down into the crust, then listens for the echoes that bounce back up. Ice and water reflect those waves differently, so as the signal travels down, every change in the material sends a faint whisper back to the antenna. The instrument can probe as deep as 30 kilometers, reading the layers one echo at a time. If there are pockets of liquid trapped inside the shell, briny lakes suspended in the ice, the radar could catch them. It maps the hidden architecture we've only ever guessed at, turning a blank white surface into something with depth and structure. And then, if the echoes line up the way scientists hope, there's the deepest reflection of all, the one from the bottom. For the first time, we may see the boundary where ice becomes ocean. But radar only shows you where the water is. To know what's in it, CLIPR has to touch it. And Europa may hand us that chance without us ever landing, because water from below doesn't always stay below. Cracks in the shell can vent, firing tall plumes of vapor hundreds of kilometers up before they fall back or drift into space. Hubble has caught hints of them more than once. If CLIPR times a flyby right, it could pass straight through one of those geysers at several kilometers per second. In that instant, instruments open their mouths to the vacuum. A mass spectrometer sorts each particle by weight, counting the atoms and molecules that slam into it. A dust analyzer catches the frozen grains and reads what's locked inside. So a single pass, lasting only seconds, becomes a sample of the sea itself. No drilling, no melting, just the moon offering up a piece of its hidden interior. And that's the quiet, unsettling part. If the ocean is alive, its chemistry would be written into every droplet it spits out. But CLIPR isn't going out there by itself. While NASA was building its plan, Europe was building a rival plan of its own. And in April 2023, the European Space Agency launched a spacecraft called JUICE. The name stands for Jupiter Icy Moons Explorer, and its whole job is to study the frozen worlds circling that giant planet. JUICE won't focus on Europa the way CLIPR does. Its main target is Ganymede, the biggest moon in the entire solar system, a world that almost certainly hides its own buried ocean under a thick shell of ice. But on its way, it'll take a couple of close looks at Europa too, sniffing the same environment from a slightly different angle. So you end up with two spacecraft built on two different continents, aimed at the same swarm of icy moons. They carry different instruments, ask slightly different questions, and they'll cross-check each other's answers. When both start sending data back, we won't be guessing from one set of eyes. We'll be reading two. Two civilizations sent robots to the same ocean, which tells you how badly we need to know. Orbiters can only do so much. They fly over, snap their readings, and move on, hundreds of kilometers above a surface they'll never touch. Everything we learn from CLIPR and JUICE gets filtered through that distance. So engineers started sketching something bolder. NASA's Europa lander concept, studied around 2016 and 2017, imagined a spacecraft that would actually set down on the crust and scoop the top few centimeters of ice into onboard instruments. Not a flyby, a machine sitting still on that frozen shell, sampling the very stuff we've only watched from orbit. And a lander is just the doorstep. The real dream sits further out, past the surface entirely. If chemistry lives in that ocean, you don't find it in the ice on top. You find it in the water below, under a crust that might run 15 to 25 kilometers deep in places. Picture a probe that melts or drills straight down through all of it, chasing liquid we've never seen. That's the vision that keeps mission planners up at night, because reading Europa from above will only ever give us shadows. To truly meet whatever lives there, we would have to break the seal ourselves. So picture the problem. Europa's shell isn't a frozen pond you crack with a hammer. It's a slab of ice that could run anywhere from a few kilometers to 30 kilometers thick, harder than granite at those temperatures, sitting at roughly -160 degrees Celsius on the surface. Any probe that wants to reach the water has to somehow move down through all of it. Melt it, cut it, burn it. Nobody agrees. And every meter you descend, the ice above you refreezes and slams shut behind you, sealing off your only way home and your only signal path to the surface. Then there's power. You can't run a hot drill on sunlight out there. Europa gets about a 25th of the light Earth does. Whatever melts that ice has to carry its own energy source down into the dark, alone, for weeks or months, with no chance of repair. Engineers have sketched ideas: heated probes, mechanical cutters, tethered machines paying out cable as they sink. On paper, some look promising, but not one has ever bored through an alien world's crust. Kilometers of ice stand between us and an answer, and we have no proven way through. Say we solve the drilling. Say a probe punches through the shell and reaches liquid water below. There's a problem riding along with it, and it's alive. Every spacecraft we build carries microbes from Earth, tucked into seams and coatings, and the tiny gaps no cleanroom ever fully closes. Some of those microbes are stubborn. Certain bacterial spores survive years of vacuum, radiation, and temperatures that should kill anything. Deinococcus radiodurans shrugs off doses of radiation thousands of times what would kill a human. Tardigrades have been revived after exposure to open space. Now imagine one of those hitchhikers thawing out in a warm, salty ocean that's been sealed away for billions of years. If it takes hold, we've contaminated the sample before we ever read it. Worse, we might not be able to tell our life from theirs. That's why NASA follows planetary protection rules, sterilizing hardware and choosing trajectories that avoid a crash into Europa. But sterilization is never perfect, and ice moves. There's a version of exploring Europa that destroys the very thing we came to find. So let's line up what we actually know, because the pieces have stopped being guesses. The ocean under Europa's ice isn't a maybe anymore. Magnetic readings from Galileo showed a salty, conductive layer sloshing beneath the shell, and the numbers point to more liquid water than every ocean on Earth combined. Then there's energy. Jupiter's gravity needs this moon on every orbit, flexing its interior, generating heat where sunlight never reaches. That same tidal squeezing could drive vents on the seafloor, the way it feeds the plumes on Enceladus. And the chemistry checks out. We've seen salts, we've seen signs of organic building blocks, and the plumes give us a way to taste that water without ever landing. Water, energy, the raw ingredients. 3 boxes, and none of them empty. Now Clipper is on its way, carrying instruments built to measure exactly these things, closing a distance of hundreds of millions of miles toward an answer we've circled for decades. Every thread pulls in one direction. Everything we have learned converges on a single image at the bottom of that ocean. So picture yourself standing on that surface. The ice under your boots is harder than granite, chilled to around 160 degrees Celsius below zero, cracked into ridges that run for hundreds of miles. Overhead, Jupiter hangs enormous and silent, and the sun is a bright pinprick, giving you almost nothing. Now go down. The first few meters are broken and refrozen, a churned rind scarred by radiation and impacts. Then the ice closes over you, and the last of that weak daylight fades into a blue that gets deeper and darker with every meter you sink. Kilometers pass. The shell here might be 15 or 20 kilometers thick, maybe more, and the pressure builds the whole way down. Somewhere in that frozen dark, pockets of briny water hide between the layers, and the ice slowly warms from bone cold towards something that can flow. Then the solid gives way to slush, and the slush gives way to liquid. You've reached the top of the ocean, and it's black, because no light from the surface ever makes it this far. Every meter down, the pressure rises and the light dies, and still we are not at the bottom. We drop through the last of the shell, and the walls stop being walls. On the way down, we pass pockets of trapped brine, veins where warmer water once cut channels through the ice and refroze. Some of those cracks run for miles, threading the crust like roots reaching for the sea. The ice here isn't the clean blue you'd picture. It's stained rusty brown in places, colored by salts and sulfur compounds that welled up from below and stalled inside the crust. Each streak is a record of water that moved, a hint that this shell has been alive with motion for a very long time. Then the ceiling above us thins to nothing, and the last chunks of ice float free instead of holding together. There's no floor beneath our lights, no wall to either side. The beam just reaches out and fades into water that goes on further than the eye can follow. We've come 15, maybe 20 kilometers straight down, and this is only the beginning of the descent. Below the ice, the water opens into a black sea, larger than any on Earth. Nothing down here has ever seen light. Sunlight dies at the top of the ice, and below that shell, there's just water, all the way down, holding a darkness that has never once been broken in 4 billion years. This ocean might hold twice the water of every ocean on Earth combined, stacked into a layer maybe 100 kilometers deep. And it's silent in a way nothing on our planet is. No waves, no light filtering from above, no surface to reach for. Near the ice, it's brutally cold, hovering just above freezing, kept liquid only by the salt dissolved in it. But the water doesn't stay that way the whole way down. The deeper the beam pushes, the more that cold starts to ease, degree by degree, as if something far below is bleeding warmth up into the black. That's the part that turns your stomach a little. On Earth, heat comes from above, from the sun. Here, it's the opposite. Cold water sinks, warm water rises, which means the floor is where the heat lives. So you follow the heat down, past miles of black water, until the light from your instruments finally catches something solid. It's rock. Not smooth, not flat, but broken and buckled, the way stone looks when something underneath it is still moving. This is the seafloor of Europa, roughly 100 kilometers below where you started drilling, and it's touching the moon's rocky interior directly, mantle pressing against ocean with nothing in between. That contact matters more than almost anything else down here. Because Europa gets squeezed, Jupiter's gravity needs the whole moon on every orbit, flexing the interior and generating heat through friction. That energy has to go somewhere, and it goes here, into the rock at the bottom of the sea. So you're standing on a warm, possibly volcanic floor, in total darkness, with water that's been chemically reacting with hot stone for billions of years, minerals leaching out, energy leaking up, a boundary between fire and water that never went quiet. This is the exact stage where, on Earth, life first stood up in the dark. So picture the seafloor now, cracks in the rock where the ocean sinks down, hits the hot interior, and comes roaring back up, loaded with dissolved minerals. That water can pour out at temperatures Earth's own vents reach, hundreds of degrees, meeting a near-freezing ocean that snuffs it back down in seconds. Where the two collide, the minerals crash out of solution and pile up. On Earth, these become chimneys, black smokers that grow like stone trees, some tall as a 15-story building. On Europa, the same chemistry has no reason to stop. And here's what matters about that clash. The hot fluid carries hydrogen, sulfides, iron, the raw feedstock of chemical energy. When it meets the cold, oxygen-touched water above, you get a gradient, a battery with two ends, and anything sitting in the middle can tap the current to build itself. No sunlight required, no photosynthesis, no surface, no sky, just rock, water, and heat doing what they've done for 4 billion years. Around Earth's identical vents, entire worlds of creatures live without a single ray of sun. So count what's down there. Liquid water, kept warm and moving for longer than anything on Earth's surface has existed. That's ingredient one, and it never froze. Heat comes free, squeezed out of the rock by Jupiter's gravity flexing Europa's core again and again. The vents pour out dissolved minerals, iron, sulfur, magnesium, the same chemical building blocks that coated the early Earth. Ingredients 2 and 3, delivered without sunlight lifting a finger. Then there's energy, the part everyone assumes needs a star. It doesn't. Where hot vent fluid meets cold ocean water, the chemistry itself releases usable energy, enough to power a cell. That's the fourth ingredient, and it's running right now. And the last one is the one that should unsettle you most: time. Europa has had roughly 4 billion years of all of this, uninterrupted, in the dark, with nothing to reset the clock. On Earth, life needed far less than that to appear. Water, heat, minerals, energy, time. With the recipe complete, only one question remains, and it is the one we started with. Go back to that needle. When Galileo swung past Europa in the late 1990s, its magnetometer caught something strange, a magnetic field that flipped and bent in step with Jupiter's own rotating field. The Moon wasn't making that field, it was echoing one. And only one kind of material bends a magnetic signal that cleanly. Not rock, not solid ice. You need a layer that conducts electricity, spread out in a shell around the whole world. Salt water does exactly that. So the needle wasn't twitching at random, it was tracing the shape of a global ocean, buried under kilometers of ice, responding to Jupiter like a mirror held up to a passing light. Every wobble was the sea underneath answering back. We built an instrument to measure magnetism around a distant moon, and what answered was liquid water we could not see and had never touched. The salt, the depth, the energy below, all of it hiding behind one bending line on a graph. That needle was not detecting a moon, it was detecting a sealed, living capable sea. So picture what could actually be down there and lower your expectations, because the truth is smaller and colder than the movies. Whatever lives in Europa's ocean is almost certainly microbial, single cells drifting in perpetual black water. No sunlight ever reaches them. They've never known a surface, a sky, or a single warm day. They'd cluster where the energy is, packed around hydrothermal vents on the seafloor, feeding on chemistry instead of light. On Earth, similar microbes pull energy from hydrogen and sulfur, building whole ecosystems in total darkness. Europa's cells might do the same, huddled in the one warm current in a 100 kilometers deep sea of ice water. And here's the part that unsettles the biologists. If life started there on its own, it wouldn't just look different, it might run on different rules, different building blocks, a different genetic code, a chemistry that shares no ancestor with anything alive on Earth. It would be life we can't quite categorize, discovered by an instrument that may not even recognize it, not fierce, not hunting, just existing, quietly, in a place that has never once seen the sun. We are not talking about monsters, we are talking about something far stranger and far quieter. So set aside the image of teeth in the dark, of something with eyes gliding up toward a probe's lights. That's the easy fear, the one built for movies. What's actually unsettling is smaller and colder than that. Think about the ingredients here: liquid water, a rocky floor, heat leaking up from below, and chemistry stirred by the tides. Those aren't rare cosmic accidents. They're the kind of conditions that show up again and again, on moons and worlds we haven't even mapped yet. Europa isn't special because it might hold life. It's frightening because it might be ordinary. If something is down there in that black water, it didn't need a perfect planet, or a gentle sun, or billions of years of luck. It just needed water and warmth touching rock. And if that's all it takes, then the same recipe is sitting quietly across the galaxy, in 1,000 dark oceans nobody has looked into. The scary part is not what lives there, it is what it would mean if anything does. Here's what makes Europa different from every other place we've talked about. Every living thing on Earth, the bacteria in your gut, the redwoods, the deep-sea worms clinging to those vents, all of it traces back to one single start, one cell, roughly 4 billion years ago, that everything else descended from. We're all cousins on the same family tree. But life inside Europa wouldn't be on that tree. It would have started on its own, from scratch, behind 15 miles of ice, with no way to trade a single molecule with us. That's what scientists mean by a second genesis. Not aliens who arrived from somewhere, but a completely separate invention of life, running its own experiment in the dark. And that's the part that stops you cold. We have exactly one example of life beginning, one data point in the whole universe. Finding a second, right next door, orbiting the same sun, would take that lonely one and quietly double it. Because a thing that happens once could be a fluke, a cosmic accident that never repeats. A thing that happens twice in the same solar system is a pattern. If life started twice in one solar system, then the universe is almost certainly crowded. So here's the question that follows us home. We've spent decades pointing antennas at the sky, listening for a signal, a whisper, anything. And what we've heard back is nothing. That quiet has a name, the Great Silence, and it's bothered scientists since the 1950s. We assumed the silence meant we were alone, or nearly so. But look at what Europa just told us. Life might not need a warm planet at the right distance from a star. It might not need starlight at all. Think about where the heat actually comes from down there. Not the sun, but the tug of Jupiter's gravity kneading the moon's interior. That kind of engine runs anywhere there's a big planet and a moon squeezed close. And those setups are everywhere. Rogue worlds drifting through the dark with no sun at all. Icy moons in every solar system we can imagine. If life prefers the deep dark instead of the surface, then we've been listening in the wrong place this whole time. Oceans locked under ice would be invisible across the galaxy, and there could be billions of them. Think about what a planet like Earth actually needs. It has to sit in a narrow band where water stays liquid on the surface, not too close to its star, not too far. It needs a stable atmosphere, a magnetic field to hold that atmosphere in place, and billions of years without a catastrophe to reset the clock. Line all of that up, and you get a thin, habitable ring around each star, and most worlds miss it. Now count the other kind. Every gas giant we've found tends to drag a family of icy moons along with it, and those moons don't care where the habitable zone is. Their heat comes from tides, from the squeeze and pull of the planet they orbit, not from sunlight at all. So the warm surface world starts to look fragile, almost like a fluke. The ocean sealed under ice looks steady, shielded, repeatable, the setup you'd expect to find again and again. If life prefers the dark under ice, then worlds like ours may be the strange exception. Here's where I have to be careful with you, because the honest version of this story is less satisfying than the one your imagination wants. We have not found life on Europa. Not a cell, not a microbe, not a single chemical fingerprint that says something down there is alive right now. What we've actually done is add up the ingredients. Liquid water, more than twice what Earth holds. Heat leaking up from a flexing core. Chemistry seeping through cracks in the ice. The raw materials for building and feeding a living thing. Every one of those boxes is checked, but conditions for life and life itself are separated by a gap nobody has crossed yet, not in a lab, not on any world we've reached. A perfect kitchen doesn't prove somebody cooked. And that restraint is the whole point. The moment we let ourselves say we know, we stop doing science and start telling ourselves a story we like. So we hold the line, even when the setup is this good, this tempting, this close. We stand at the edge of the answer without yet being allowed to read it. Think about where we actually are right now. For the first time in human history, we have a testable question about life beyond Earth, and a real shot at the data to answer it. Not a hunch, not a hope pinned to a telescope smudge, but a target 628 million kilometers out, with the right ingredients in the right place. That's the strange privilege of this moment. Generations wondered if we were alone and had nothing but the sky and their imaginations. We get to ask the same question with a spacecraft built to sample the very ocean we're arguing about. And the difference between wondering and knowing has never been this thin. The answer could take years to arrive, It might come back empty, a quiet ocean with chemistry and nothing swimming in it. Or it might come back as the single most important measurement anyone has ever made, and we honestly don't know which, and that not knowing is the whole point. So we wait at the threshold, patient, hands off the conclusion. The instrument that could settle it is already crossing the dark toward Jupiter. Clipper reaches the Jupiter system around 2030, and it won't just glance at Europa once. It's built for roughly 49 close flybys, some skimming as low as 25 kilometers above the surface, each one feeding back a slice of a world we've only ever squinted at from far away. That cadence matters. One pass gives you a hint. 50 passes, layered together, start turning hints into a picture. Ice thickness, the chemistry venting off the surface, the shape of whatever ocean sloshes underneath, all of it sharpening flyby after flyby. So the timeline is real, and it's short. Within a handful of years, the answer we've circled for decades could tighten from maybe to almost certainly. Not proof of life, not yet, but the conditions for it, measured instead of guessed. And that's the strange edge we're standing on right now. The data is coming. The instruments are already out there in the dark doing the work. We just haven't been handed the result. We may be the last generation to look at Europa and honestly say we do not know. So here's the thing we've been circling this whole time. For most of human history, the nightmare we told ourselves about space was the empty one. A cold, silent universe with nobody in it but us. 100 billion galaxies and not one other pulse. But Europa flips that fear on its head. Under 15 to 25 kilometers of ice, in an ocean that stayed liquid for maybe 4 billion years. The scarier possibility isn't that nothing's there. It's that something is, and it has been the entire time, with no idea we exist. Think about what that actually means. A biosphere sealed under a shell, going about its chemistry in the dark, while we point telescopes outward looking for radio signals. We've been listening for a knock at the door, when the neighbor was living downstairs the whole time. That's the specific weight of this place, not the void, not the monster, just the quiet chance that we've never once been the only thing alive, and we couldn't tell. Europa is terrifying because it might not be lonely, and neither, then, are we. Sit with that for a second. In 1610, Galileo pointed a homemade tube at Jupiter and saw 4 faint dots drifting night to night. One of them, the third out, was Europa. Just a smudge of light he could barely hold steady in the eyepiece. For 400 years, that smudge stayed a curiosity, a name in a textbook, a moon we filed under interesting and moved on. And the whole time, if the ocean below the ice is doing what we now suspect, something down there was going about its business in the dark. Not waiting for us, not aware of us, just alive. That's the weight of it. A dot from a 1610 telescope, sitting in an ocean we can't see, possibly holding the second time life ever started in this solar system. If that's true, it happened twice, independently, within reach of the same sun. And once you actually let that land, it stops being a fact about a moon. A discovery like that would not stay in a science journal, it would change how you see the sky. So picture where you'd be. Maybe you're pouring coffee, half listening to something in the background when the words come through. Not aliens landing, not a signal, just confirmation that something is alive under 15 kilometers of ice, 628 million kilometers away. You wouldn't feel it in your body the way you feel news that touches your own street. It's too big and too far for that. And yet some quiet part of you would understand that the number of living worlds you know of just went from 1 to 2. That's the strange thing about a discovery like this. It arrives without a sound, without a face, without anything to point at in the sky. You'd walk outside that night and Jupiter would look exactly the same, a pale dot you've seen 1,000 times, holding a secret it held long before anyone was here to ask. People would go to work the next morning. Traffic would still be bad, but the frame around all of it would have shifted, quietly, permanently. That moment could arrive in your lifetime, on an ordinary day, from a machine far away. Picture how it might actually land. Not a trumpet blast, not a screen full of aliens, but a single line buried in a status report from a spacecraft orbiting 628 million kilometers away. A chemical signal in the plume, a number that shouldn't be there, flagged by an instrument doing its slow, patient work. Then a press release, careful and hedged, full of words like candidate and consistent with. Scientists would argue for months, maybe years, running the checks again, ruling out contamination, waiting for a second pass to confirm it. That's how the biggest news in human history would probably arrive, wrapped in caution. And you might read it on your phone between emails, half distracted, before the weight of it caught up with you. A Tuesday. Coffee going cold, the dishwasher running. Somewhere out past Jupiter, a machine had just quietly rewritten our place in the universe, and the sky outside your window looked exactly the same. We'll sit with that a moment, then let it go, because whatever the answer, the question alone has already changed what Europa means. For a long stretch of human history, we assumed life needed sunlight, warm shores, and a sky it could see. Europa breaks every one of those assumptions. It's a world with no sunlight reaching its depths, wrapped in ice miles thick, and yet it might hold more liquid water than every ocean on Earth combined. That shift matters more than it first sounds. If life can start under 15 kilometers of ice, warmed by nothing but tides and rock, then the places we can rule out get much smaller. Every icy moon, every rogue world drifting between stars, suddenly moves onto the list. So Europa becomes a hinge point. On one side, the old idea that life is a rare accident that happened here and maybe nowhere else. On the other, the possibility that oceans like this are scattered across the galaxy, quiet and dark and full. We don't have the final answer yet, but the question has already moved from whether life is rare to whether we've simply been looking in the wrong places. To see how far we have come, it helps to look back at where we started tonight. Think back to that first smudge of light, a dot creeping across a telescope's field of view, night after night. For centuries, that's all Europa was, a moving point beside Jupiter, one of 4 that shouldn't have existed if Earth sat at the center of everything. Then the flybys came. Voyager caught those long, dark cracks running for hundreds of miles, and suddenly the dot had a face, cracked like a shell that something had pushed against from the inside. Galileo did the harder work through the 1990s, drifting close again and again, reading the way Jupiter's magnetic field bent around the moon. That bending only made sense if a salty, conducting ocean was sitting under the ice, sloshing in the dark. So the picture sharpened in stages. A light became a world became a frozen surface, and a frozen surface became a lid over roughly twice the water in all of Earth's oceans. From 4 lights in 1610 to an ocean in 2000, the story only accelerated from there. So let's hold on to what's actually confirmed, because it's solid ground. Beneath that shell of ice sits a global ocean of liquid salt water, and it's been there a long time. Magnetometer readings from the Galileo spacecraft in the late 1990s clinched it. As Europa moves through Jupiter's magnetic field, something inside it pushes back, and the cleanest explanation is a conductive, salty sea. We know what keeps that ocean liquid so far from the sun. Jupiter's gravity stretches and squeezes Europa on every orbit, and that flexing generates heat from the inside out. It's called tidal heating, and it's the same engine that lights up volcanoes on the neighboring moon Io. We also know the rough chemistry is plausible. The rocky seafloor likely touches that water, and rock meeting warm salt water tends to release the raw ingredients life elsewhere has used. Not proof of anything living, just the right pieces sitting in the same room. A salty sea, a steady source of heat, and a seafloor that could feed it. Those are the facts, and the facts alone are already extraordinary. But here's where the facts run out. We don't know if anything actually lives in that ocean. Not a microbe, not a single cell. The ingredients being present is not the same as life showing up to use them. We don't know how thick the ice really is. Estimates run anywhere from a few kilometers to more than 20, and that number changes everything about how we'd ever reach the water below. A thin shell means the ocean is almost within arm's reach. A thick one means it's locked away under a wall we can't yet drill through. And those plumes, the ones that supposedly vent water out into space, we're still not sure they're reliable. Some observations hint at them. Others come up empty in the same spot months later. We can't say for certain they erupt on a schedule, or even that they erupt at all. So we sit with a strange kind of honesty. We know enough to be certain something interesting is down there, and not enough to say what. The gap between what we know and what we want to know has never been narrower. Here's what actually changes if we find something living under that ice. For all of human history, every organism we've ever met traces back to a single origin. One tree, one root, one-time life started on one rock. A second, separate start on Europa would mean life isn't a fluke that happened once. It'd mean the universe makes life whenever the conditions line up. Think about the scale of that. Europa is one moon, orbiting one planet in one solar system, in a galaxy holding maybe 100 billion stars. And that changes everything about the odds. The silence we've always assumed suddenly looks a lot like us not having listened hard enough yet. You'd wake up in a universe that felt fuller than the one you fell asleep in, not because anything out there moved, but because the number in your head changed. The word alone would mean something different than it did the day before. This is not a distant abstraction, it is a question about your place in everything. Think about what actually changes if we find it. Not the technology, not the headlines, but the quiet reordering that happens inside a person when they learn they were never the only chapter. For centuries we assumed life was a fluke that happened here and nowhere else within reach. A second, independent origin, right next door, hiding under 15 to 25 kilometers of ice, would end that assumption in a single afternoon. It would mean life isn't rare or precious in the way we told ourselves. It springs up wherever there's water, warmth, and time. That's a humbling thought and a strangely comforting one. We'd be smaller, one species on one world orbiting one ordinary star, and also less alone than we've ever felt. The same chemistry that built us would have quietly built something else, in the dark, without permission or witness. And it wouldn't need to be clever. No cities, no signals, no eyes looking back. Just one living cell, drifting in an ocean we can barely imagine. A single microbe on Europa would rewrite the story of life itself. Right now, Clipper is on its way, gliding through the dark toward a world it won't reach until 2030. When it arrives, it won't land. It'll loop around Jupiter and swing past Europa nearly 50 times, each pass skimming as low as 25 kilometers above that cracked shell of ice. On every flyby, its instruments go to work. Radar built to see through kilometers of frozen crust, cameras sharp enough to map the surface, and sensors sniffing for the faint whisper of water molecules flung up from below. Piece by piece, pass by pass, the picture sharpens. None of this happens fast. Space runs on patience, on years of quiet cruising and careful calibration. But somewhere in that stream of data, the answer we've chased for decades might finally surface. And here's the part worth sitting with. You're alive at the exact moment we get to look. Not a generation that only wondered, but one that gets to find out. The results will unfold in the coming years, and they are worth paying attention to. So picture it now, while our spacecraft coast and our instruments warm up. Down there, under 15 to 25 kilometers of ice, the water keeps moving. Slow currents, warmed by the tug of Jupiter, circling in the dark, the way they have since before Earth had continents. No sunlight ever reaches it, no storms cross its surface. Just a shell of ice overhead, cracked and healed, and cracked again, and beneath it, maybe twice the water of every ocean on our planet, holding whatever it holds. If something drifts through that black water, it has never seen a star. It doesn't know we exist, doesn't know we're building the thing that will finally listen. It just goes on, the way it always has, fed by chemistry and heat leaking up from the rock. That's the strange part. This ocean isn't waiting for us the way we're waiting for it. It kept its secret through the whole history of life on Earth, patient in a way nothing living could match. It waited 4 billion years, so it can wait a little longer for us to arrive. So think back to that needle, that thin line on the magnetometer, twitching in the dark as Galileo swept past Europa in the late 1990s. Back then, it looked like noise, a jitter engineers had to explain away, a wobble in a graph nobody could quite account for. We know now what was tugging on it, a conductive layer buried under the ice, salt water bending Jupiter's magnetic field the way seawater would, a signal that only makes sense if there's an ocean down there, roughly 100 kilometers deep. The needle wasn't glitching, it was reporting. Read it again with everything we've learned, and it stops being a puzzle. It becomes contact. A hidden sea, sealed under kilometers of ice for 4 billion years, reached up through Jupiter's field and left its fingerprint on our instrument, before we even understood what we were holding. That trembling needle was the ocean waving, and we are only now learning to wave back. Go back to that night in January 1610. Galileo tilts his handmade telescope toward Jupiter and sees 4 little points of light strung out beside it. One of them is Europa. To him, it's a smudge, a companion star, a curiosity worth a few lines in his notebook. He had no way to know that Speck was a frozen shell wrapped around a saltwater sea deeper than every ocean on Earth combined. No way to know it had been hiding liquid water for 4 billion years. It was just a dot, one among 4, easy to lose against the black. Now that same dot has a name, a map, a magnetic signature, and a spacecraft built to chase it. We've measured its pull, traced its cracks, and watched it bend Jupiter's field. Europa Clipper is already on its way to circle back, again and again, listening. 4 centuries turned a footnote into the most watched ocean in the solar system. The faint light, Galileo shrugged off, is the one we can't look away from. The dot that meant nothing in 1610 may soon mean everything. So here's where we stand. Under maybe 15 miles of ice sits an ocean twice the volume of every sea on Earth, kept warm by a planet's worth of gravity squeezing a moon. We've traced the salt, the plumes, the fresh cracks. We just haven't looked inside. That's the part that sits with you. Not the fear that something's down there, but the quiet chance that it is, and that we're the first generation with the tools to find out. Everything we've talked about points to one closed door, and the key is already in flight. We don't get to know the answer tonight. Nobody does yet. But that streak of light Galileo saw in 1610 and waved off as nothing is still up there, circling Jupiter, holding whatever it holds. So the next clear night, find Jupiter. Look for the faint dot beside it, the one that meant nothing 4 centuries ago, except now you know an ocean is waiting under the ice, and we're finally on our way. If you want to be there when we knock, stick around and keep looking up with us.